For centuries, alchemists and scientists were captivated by quicksilver. It is a liquid metal that beads up, darts across surfaces, and slips right through your fingers the moment you try to grasp it. Today, modern science is hunting two entirely different targets that share that exact same name. One is a toxic heavy metal that poses a severe threat to human biology. The other is a scorched, barren planet holding the secrets of our inner solar system. Despite the vast difference in scale, both of these targets share a defining trait. They are highly hostile to human observation, and they actively evade capture. Here on Earth, the element Mercury actually begins its journey locked away in a solid state. It is most commonly found bound deep underground within a red mineral called cinnabar. But the threat arises because it almost never stays that way. To protect our ecosystem from a shape-shifting pollutant, and to understand the violent origins of our solar system by reaching that innermost rock, we have to track down two of the hardest targets in nature. The terrestrial chase begins when human activity forces that solid Mercury out of the ground. When we burn fossil fuels like coal, the intense heat breaks the chemical bonds holding the inorganic Mercury together. Coal-fired power plants alone account for nearly 44% of all human-caused mercury emissions in the United States. These massive facilities pull the element from the Earth and pump it directly into the sky. Once it hits the outside air, the element executes its primary evasive maneuver. At standard room temperatures, exposed mercury evaporates, transforming into a completely invisible and odorless toxic gas. The vapor catches a ride on atmospheric wind currents, entering the global cycle. It drifts across oceans, undetected. Eventually, rain drags these particles into water, where microorganisms absorb the vapor and attach carbon, creating methylmercury, a highly toxic organic compound. Methylmercury is perfectly designed to bioaccumulate. As small organisms are eaten by fish, and those fish are eaten by larger predators, the toxin concentrates. By the time it reaches an apex predator like the Florida panther, the concentration in the bloodstream is highly lethal. Its ability to shift from a solid rock into an invisible gas and then hitch a ride up the food chain makes it the ultimate stealth attracker of the nervous system. Deep in space, tracking the planet Mercury presents an entirely different set of evasion tactics. Because the planet orbits so close to the Sun, chasing it means plunging directly into our star's immense gravity well. You cannot simply point a rocket straight at the inner solar system. The Sun's gravity accelerates any incoming object so violently that a probe would either shoot right past the planet or continue accelerating until it burns up completely. To solve this physical interception problem, the European and Japanese space agencies engineered the BepiColombo mission. It is a highly specialized multi-module spacecraft designed to catch a fast-moving target in an incredibly hostile environment. To match speeds, BepiColombo takes a massive, looping 8-year flight path through the inner solar system. The probe performs 9 separate gravity assists, skimming past Earth, Venus, and Mercury, using their gravitational pull as a brake to bleed off velocity. Surviving this long cruise near the Sun requires heavy-duty hardware. The spacecraft relies on a bank of continuous low-thrust ion engines for precise braking, while constantly hiding behind a custom sun shield that keeps the internal instruments from melting inside what engineers describe as a literal pizza oven. The planet is protected by the extreme physics of orbital mechanics, operating much like the chemical state shifting that protects the toxic element on Earth. When a probe sheds enough speed to enter orbit, the target comes into sharp focus. Mercury is a desolate, heavily cratered rock under stark lighting, but the data reveals a bizarre gravitational lock with the Sun. The planet exists in a 3-to-2 spin-orbit resonance. That means it completes exactly 3 rotations on its axis for every 2 trips it makes around the Sun. If you were standing on the surface, you would witness an impossible sky. The Sun would rise in the east, stop dead in tracks, move backward toward the horizon, stop again, and then continue its normal journey, all within a single Mercurian day. Because the planet lacks any thick atmosphere to scatter the light, that massive Sun sits against a pitch-black sky, even at high noon. And if you look out into that darkness, Venus appears completely illuminated, acting as a brilliant full-disk beacon.
The decades of calculation and billions of dollars to reach this inner orbit are rewarded by exposing a reality that entirely defies our earthbound logic. Back on Earth, the hunt for the toxic element yields its own hard-won rewards. By requiring industrial facilities to report their chemical releases through the Toxics Release Inventory, regulators were finally able to map and corner the invisible vapor. This line chart tracks the direct result of those mapping efforts. It shows a steep 95% drop in mercury emissions from municipal and medical waste incinerators, as new tracking rules forced plants to capture the gas before it ever escaped. For the methylmercury that remains cycling through our oceans today, careful observation allows us to navigate the hazard. By analyzing tissue samples, researchers publish dietary guidelines that tell us exactly which fish are safe to eat, keeping the neurotoxin out of our bodies. Whether it is a toxic vapor drifting invisibly through our watersheds or a scorched rock racing around the sun 60 million miles away, our environment is filled with moving targets. But with patience, precision, and sheer human ingenuity, we have the capacity to track, intercept, and understand the most elusive forces in nature.